In this video, we are going to talk about what a function is and function notation. So on the warm-ups, I'm asking you to factor it for number 1, 2 to solve, and then on number 3, what is the difference between questions 1 and 2? When you're asked to factor a trinomial just means it has 3 terms. As you look to see if that particular trinomial is a quadratic. Quadratic means the highest power is 2. And this is a quadratic, and it's a trinomial. So when you're factoring this, we look to the constant term, and that's going to tell me whether or not my signs are the same or the signs are different. Because it's a negative 24, that means the two numbers I multiply to get that constant is going to be different. I'm going to have different signs. One's going to be a positive number, one's going to be a negative number. So then if it's a negative 24, I think of what two numbers multiply together to get negative 24. And I know that negative 1 and 24, or the opposite, positive 1 and negative 24. 2 and 12, 3 and 8, and 4 and 6, one being positive, one being negative, will get me 24. And then the next thing I'm going to do is look at my middle term here, the one that is attached to x, not x squared, but just x. And I know that my two numbers have to multiply together to be 24 and negative 24, but when I add them up, they have to be a negative 5. So in other words, I'm looking for a difference. The only ones that have a difference of 5 is 3 and 8. So those are my two numbers I'm going to use to multiply to get 24. And have a difference of 5. So this will factor into x, and it's going to be minus 8 because I need to have a negative 5 when I add them together, and then x plus 3. So there it is in factored form. If we take a look at number 2, it is a plus 6. So I know I'm looking for two numbers that will have the same sign, and the sign that it's going to be is positive because the coefficient on the x, or the middle term, is positive. So I know two numbers that have to add up to 5 that multiply and become 6. So once again, I can list my numbers of 6. So 1 and 6, and 2 and 3. And the only two numbers that when I add them together is 2 and 3. So this is going to factor into x plus 2, then x plus 3 is equal to 0. But I don't stop there because I'm asked to solve it. So I'm going to set each factor. X plus 2 is equal to 0, and x plus 3 is equal to 0. So x is equal to negative 2, excuse me, and x is equal to negative 3. So my final answer is x is equal to negative 2, or negative 3. I can write it as x equals. Or I can use a solution set, which is negative curly bracket, negative 2, negative 3. And so that's my solution, negative 2 and negative 3. Ideally, I would have put them in order. But the difference between 1 and 2 is that with the number 1, I am just asked to factor. And that's it. I'm not asked to solve, I'm just asked to factor. Whereas problem number 2, not only am I asked to factor, then I have to go further and set each factor to 0 and solve for x. And so my final answer is going to be a list of numbers that make this equation right here in number 2 to be true. And so the two numbers that make that a true statement is either negative 2 or negative 3. So that's the difference between questions 1 and 2. Now, the reason I went through all of that is just kind of a warm-up, and we're going to use some of those skills as we go through today's lesson. We're going to start with what a relation is, and then what a function is. And what a relation is, it is a map or a set of rules that get us from the input or the domain. So the domain, the input or the domain, and I'm going to do something to it. I'm going to have a set of rules that tells me I'm going to do something to that domain, and I'm going to get, when I get done, I'm going to get the output or the range value. Oh, you can think of it as a map, or you can think of it as a set of rules. When we're talking about math in particular, you may see something that is y is equal to 3x plus 1. What the rule is you're going to take some input, you're going to multiply it by 3, and then you're going to add 1 to that answer. And so that is the rules, or the map, to get from my input, which is x, and then my output, which is y. That's my rule. Now, if the rule is set so that each domain value is associated to one and only one range value, then we can say that that particular rule or relationship is a function. Now we're going to spend most of this class in the land of functions. And in fact, until you get past calculus, you're going to spend most of your time in functions. Not always, not all of the class is going to be in functions, but most of what we do is in functions. So if I'm asked to determine whether or not my relationship is a function or just a relationship, then what I'm looking for is a repeat in my values for x. So these are ordered pairs. So I have 1, 2, 3, 4, 5 ordered pairs. And so I have a relationship. I don't know what the relationship is. I don't know what the rule is to get from my x value into my y value. But what I do know is my x is my input, and my y is my output. So in terms of ordered pairs, the ordered pair would be when I see x comma y, then I know that my x is my input and y is my output. So I want to make sure that my x's are not repeated, that I don't have an x associated to two different outputs or two different y values. So I go along my x values and I see -6, no other -6. I see 6, no other 6. I see 3, I see no other +3. I see -3, I see no other -3. And I see 0, and I see no other 0. And when I'm talking about the 0, the -3, the 3, the 6, and the -6 is I'm looking to make sure that those numbers are not repeated in the x position in the ordered pairs. In other words, those outputs are not repeated. And since they're not, I know that A, yes, is a function. Take a look at B, and I see -2, no other -2 in the x position. I see 5, oh wait, I see 5 here. So I see 5 in two places. So I have 5 is associated to 7 and 5 is associated to -2. Because that breaks the rule of how we define a function, this one is not a function, so that's a no. If I have it in a chart, I'm looking for my x values. My x values in this particular chart is the top row. So I can see that 3, 6, and 9 are not repeated in my chart in the x positions. So this one is also a function. So this one is yes. Now, the giveaway on this also, without doing any work, is that they are using something called function notation. You'll see f, in this case x, we call x the argument. So this part right here, inside the parentheses, is the argument. In other words, that's my input. And so I know it was a function without doing any work. If I know for certain that the relationship or the map is a function, if I see y equals, I can replace it with f of x once I know that that is truly a function. So our input are independent. We get to choose values for x. That's why we call it the independent. And we call those the domain values. Those are the values we get to choose, and then we get to plug in and then do some sort of map, do some sort of rule, and then what ends up coming out is the outputs or the dependent. It's going to be dependent on what I put in, and we call those the range. So if I'm asked to graph the function x f of x is equal to x squared plus 1. Because I'm using this notation right here, I already know it's a function. So what that means is it's going to pass the vertical line test. There's not going to be more than one x associated, or this x is not, one single x is not going to be associated to more than one y. So if I'm asked to graph this with a chart, then I have x and f of x, which happens to be x squared plus 1. I get to choose any values I want for x, as long as, of course, I put it in there and it makes it a real number. So I usually choose numbers around the origin. So -3, -2, -1, 0, 1, 2, and 3. So I put in -3 into the function, so -3 squared plus 1. And that's going to give me 9 plus 1, which is 10. So the ordered pair is -3, 10. I'm going to put in -2 into my function. So I put in -2, I get 4 plus 1, which is 5. So my next ordered pair is -2, 5. I would put in -1. -1 squared plus 1 is 2. And then 0, I get 1. 1, I get 2. 2, I get 5. And 3, I get 10. So I come over here and I'm going to put my points on my chart. So -3, 10 is not on there, but -2, 5 is. So here's -2 and 5. -1 and 2, 0 and 1, and then my numbers on the other side. So this is what my function looks like. And it's a quadratic. So that's how you do it by doing it by ordered pairs. Now, because of the way that we define a function, because we define a function that for every x there can be only one y associated to it, it has to pass, graphically, it has to pass the vertical line test. So as we take a look at this and we're trying to determine whether or not these are functions, well, when I drop a vertical line on A anywhere along the graph, I'm only touching it once. So this is a yes, it is a function. If I take a look at B, if I drop a vertical line on this portion of the graph or this portion of the graph, then it looks like it is a function. But I have to be able to drop that vertical line anywhere across the equation or the graph, and right there, as you see, not only did I pass it once, I passed it 3 times, so this is no, it is not a function. Same thing goes for C. If I drop a vertical line just right there on the edge or the vertex of a parabola shape on its side, or parabolic shape on its side, then that seems to be like it is, but when I draw it somewhere else along the graph, I hit it twice, so this is also no, that is not a function. D fails, because it's going to hit it twice. E is okay, though. No matter where I drop a vertical line or draw a vertical line, it's fine. And then on F, if you're thinking, no, it's not, in reality it is, because, let me zoom in on it, is that this one is solid, so it's inclusive, but because this one is an open dot, when I draw a vertical line through this, the only place it's touching is up here on the closed dot, because it's really not touching right there because it's an open dot. So even though my initial reaction is like, wait a minute, I don't think so, the answer is yes, this is a function. So then, if I'm asked to evaluate, one of the ways that I can ask to evaluate is using function notation. So if I know this is a function, then I can just put that value in and evaluate it. What you would have seen prior to function and notation is you would have seen something like x squared minus x minus 2. Find the value when x is equal to 2. And then I'd have to write that every time, right? I'd have to say, and find the value of this expression when the value, find the value of the expression when x is equal to 2. Now that's a lot of writing. So because I'm not real fond of a lot of writing, then we get to use function notation. So function notation means exactly what I just wrote, or just erased. It says, hey, here's this expression, x squared minus x minus 2, and I'm asked to evaluate it when x is equal to 2. So everywhere I see x, right here, I'm going to replace it with -2 or +2. So +2 squared, and then minus. I'm going to replace this with 2, so minus 2. And then minus 2. So I have 4 minus 2 minus 2, which gives me 0. Now, when I'm asked to evaluate for a negative 2, I'm going to do the exact same thing. I am going to make sure I pay attention to the negative. So this is going to be equal to negative 2 squared minus negative 2 minus 2. Now, notice with A, I could have got away with not putting the 2 in parentheses because it's positive. But when I see the negative here, I always put this in parentheses because I have to remind myself this very first term right here is negative 2 squared, so that becomes a positive 4. And then minus a minus, that's here, minus a negative number becomes a positive 2, and then minus 2. And so my answer here is 4. So pay attention to your negatives because it can really mess you up. Okay, now let's take a look at C. With C, I'm going to substitute wherever I see x. I'm going to substitute x plus 3 now. So remember my function was, I'm just going to rewrite it right here. My function was f of x is equal to x squared minus x minus 2. So wherever I see, that should be h of x. So let me change that from f to h. So wherever I see x, I'm going to replace x here with the x plus 3 and also right here. So this is going to be equal to x plus 3, the quantity squared, minus x plus 3 minus 2. Now, this is one of those things that we hope that you come into with this class with the knowledge of, but if you don't, that's okay, because I will go over them. This is what we call a perfect square trinomial. It is of the form a plus b, the quantity squared. When you multiply this out, it becomes the first one squared, the first term squared, so a squared, plus, and that's only because it's a plus b, 2a, and then multiplied by b, so 2 multiplied by the first term times the second term, and then plus my second term squared. So this is a perfect square trinomial. So I know that when I do x plus 3, the quantity squared, this is going to multiply out into x squared, that's my first term, plus 2 multiplied by x multiplied by 3, plus 3 squared. So that's that part of it. Now I've got to remind myself that there's a negative 1 here that's going to distribute onto the x and onto the 3. So then that's going to be minus x minus 3 minus 2. So this is going to be equal to x squared plus 6x, the 2 and the 3 gives me 6x, plus 9 minus x minus 3 minus 2. Now I'm going to combine up like terms. I only have one x squared, so that is x squared. But I have the 6x and this minus x that gives me positive 5x. And then I have the 9 minus 3 is negative 6, minus 2 more gives me positive 4. So this is my final answer. All right, so the difference between A from number 1 and number 2 is that number 1 I am putting values in and I'm finding the outputs. Now you notice on C my output happened to be equation, and that's okay. We like it when our outputs are numeric values, but if it's an equation, that's okay too. But on number 2, it says I have the output. And the reason I know I have the output is because I have k of some unknown is equal to, that equal to, it says I have the y value. So if I come back up here and I just rewrite this as h of negative 2 is equal to 4. What that tells me is when I put in 2, negative 2, 4 comes out. So that's what it would look like in an ordered pair. But in this form, because I have k of t is equal to 2, then what that means is I am chasing the x value or the t value that produces 2 as the output. So I'm going to do this one differently. I'm going to write this as t squared plus t is equal to 2. And so this is a quadratic, and I know it's a quadratic because I see a squared there, so I'm going to treat it as such, which means I need to bring the 2 to the other side. So t squared plus t minus 2 is equal to 0. Now, you're thinking, that's how come she did the warm-ups. Yes, this is how come I did the warm-ups, is not only am I going to factor this, but I'm going to actually solve for the t values that produce 0 when I put it into this function. So factoring this, I have t minus 2, t plus 2, and then t minus 1 is equal to 0. That means t is equal to negative 2 and t is equal to 1. Those are the two answers that when I put t in negative 2 into this function, and when I put t is equal to 1 into this function, I will get 2 out. So those are my two answers. And again, I can write it as t equals, or I can use curly brackets to show I have a solution. Now, if I take a look at B, it's the same kind of thing. This is telling me I have the answer of 12. So t squared plus t is equal to 12. Same kind of thing as I did before. It's a quadratic. I'm going to bring 12 to the other side. So t squared plus t minus 12 is equal to 0. So t plus 4, t minus 3 is equal to 0. So my two values are t equals negative 4 and 3. Curly brackets, 4 comma, negative 4 comma 3. Erase that, and 3. Okay, so pay attention to the notation. The notation is really important. If I see k of t or h of t or f of x equals a number, that means I have the output and I'm chasing the input. But if I see it as h of negative 2, or I see it as, in this case, k of 3, then I'm asked to find the output that is associated with the x of 3. All right, so now let's take a look if I were given the graph. If I were given the graph and I'm asked to figure out what the solution is, I know when I have f of negative 1, that is my x value. So this is saying when x is equal to negative 1, what is the y that is associated to it? So I come to negative 1 on the x-axis, and then I go either up or down until I find my graph. In this case, I go up because it is above my negative 1. And then once I hit my graph, I'm going to go across to the y-axis to determine the value that is associated to that negative 1 when I put it in, and the answer is positive 1. So if I come up here and they're asking me to evaluate f of negative 1, this is the same thing as 1. My output was 1. On my second part here, they're giving me the y value. So I go to the y value right here, and then I'm going to go across my graph until I hit my graph. And then once I hit my graph, I come straight down. So I go first from my y value, and I go left or right until I touch my graph, and then I go down or up, in this case I went down, to the x-axis to figure out what y value is associated to that. So the answer to this one, for the second part, is when x is equal to 8, my output, f of x, is equal to 3. So in other words, my ordered pair is 8, 3. Just like up above, my previous example, my ordered pair was negative 1, 1. We're going to determine whether or not a function is one-to-one later in this chapter. Right now, we're just going to let it go for right now and just say, hey, if it's one-to-one, it has to pass a horizontal line test besides the vertical line test. And then if you want to read up on it now, that's totally cool, or otherwise you can just wait until we get there. Now, what we talked about in class today is we did start looking at the basic, we call these the basic toolkit functions. You might also hear them as the parent functions. And so we have certain names. The first one, this is a constant function. That's the name of it. What it looks like is f of x is equal to some number. It's just a number. There's no x attached to it, just a number. And when that happens, it's a horizontal line. Okay. The next one that you should know is the identity function. That's the name of it. And what it looks like is f of x is equal to x. And the reason this is the identity function, because when I do f of -3, -3 comes out. When I do f of, say, 17, 17 comes out. So whatever my x value is, it's the same thing as my y value. Now it's a line. It is not a horizontal line. It's a line that goes through the origin and has a 1, 1 slope. So the change in x and the change in y gives me my slope, which is the change in y over the change in x, which is my slope, and this happens to be 1. So when I put in -3, like I did before, so I put in -3 for x, and then -3 comes out for y. So it is a 1, 1 slope, and we call this the identity function. Any equation that is a line that is not horizontal, so as an example, y is equal to 3x plus 5, this is a transformation of the identity function. We're going to explain what transformations are later in this chapter, but just think that every time you have an equation of a line, it is a transformation of the identity function. The next one we're going to look at is the absolute value function. That's the name of it. And it is f of x is equal to the absolute value. The absolute value, if we are not looking at it on the xy plane, absolute value represents the distance any number is from 0. So for this, if I put in a -3, go up to my graph, I'm going to come out and it's going to be +3. Because the distance -3 is from 0 is 3, and that's the y value. Now notice it also goes through the origin. The slope on this right-hand side of the turning point at the origin is a slope of 1. It is up 1 over 1. They're both being positive. Now if I take a look on what's happening on the right-hand side of the graph of the turning point as I come down into the turning point, this is a slope of -1. So all of these absolute value functions without transformations will have a single turning point. In this case happens to be the origin. And one side will be a negative slope coming in, and the other side will be a negative slope coming out of the turning point. The next one we're going to look at is the quadratic. And that's kind of like what we started out with. We had a quadratic. Now, our quadratic we had as an example was a transformation of this parent function, or the Toolkit function quadratic. All quadratics without transformation should go through the origin, and we call that the vertex. It actually has a name. It's called the vertex. And it also should go through the point 1, +1, and it should go through the point -1, +1. It also should go through the point -2, +4, and then 2, +4. Without transformations, every quadratic should look exactly like that. So from the vertex, I should go over 1 and up 1, over 1 and up 1. And I should also go over 2, up 4, and over 2, up 4 to get those ordered pairs. And we're going to really hit quadratics later in the quarter. So we'll really spend time on that. My next one that we are going to look at is the cubic function. The cubic function also goes through the origin. It has the point 1, +1, but when I put in a negative, unlike this quadratic, it has a -1 output. And that's because I'm doing -1 cubed, which is -1 multiplied by -1 multiplied by -1, which gives me -1. If I put in 2, 8 will come out because it's 2 times 2 times 2. When I put in -2, -8 will come out. So I'm cubing my number, and then whatever the sign is, whether it's a positive number or a negative number, it's going to have that same sign as the output. So notice on this side of the origin, these are all positive answers. And then on the left-hand side of the origin, these are all negative answers. And then the last one we looked at today in class was the reciprocal function. The reciprocal function is 1 over. So another way we can write this is f of x is equal to x raised to the negative 1. Reciprocal function. Now notice that as I put in 1, 1 comes out. So if I put in 1, 1 comes out. I put in negative 1 comes out. And other than that, every time I put in a whole number, or any number after 1 or any number before 1, I may not get a nice integer number because it is the reciprocal. So when I put in 2, I get 1/2 out. Nope, that's not the one I wanted to highlight, so just a minute. Let me erase that. I was actually looking at the y value. So when I put in 2, 1/2 or 0.5 comes out. When I put in -2, negative 1/2 or negative 0.5 comes out. Because it's a reciprocal. Because it is, when I put in 2, this is 1 over 2. But notice when I put in 1/2, the reciprocal of 1/2 is 2. So on the right-hand side of the graph, these are all positive. As I get closer to 0, my numbers become larger. As I get further away from 0, my numbers or outputs become smaller. As I look on the other side of the 0, as x gets closer to 0, my numbers get smaller. Although it looks like you want to say, wait a minute, but those numbers are big. Well, they're big negative numbers, which means they're small. Their magnitude is large, but their output really is small. And then, of course, and I go in the other direction as my x's become smaller, as I go to the left, they become smaller. My y values get closer and closer to 0. Now with the reciprocal function, because I have x, f of x is equal to 1 over x, I can't do f of 0 because it does equal this. So let me change it. It does equal that. Let me get rid of that. So it does equal f of x, or f of 0, erase that. So f of 0 does equal 1 over 0. However, 1 over 0 is undefined. So I never get to put in 0. So even though I want to put in 0, I don't ever get to put in 0 into the reciprocal function. Because I'm never allowed to put in 0 into the reciprocal function, I'm never going to have an x or a y value equal to 0 without a transformation. So this y equals 0 is where we get close to on our outputs, but I never actually equal that. And as well, because I don't get to have x is equal to 0, then I'm going to get close to that on my outputs, but I'm never going to equal that. So I know for my domain, which we're going to talk about, my domain for the reciprocal function is, in interval notation, is negative infinity to 0, 0 to infinity, or I may use set builder notation x such that x does not equal 0. We're going to talk about domain and range a lot more in the next section. And tomorrow in class, we're going to pick up these last couple of ones that we haven't had a chance to look at. And we'll talk about the question to ponder. So that's the lecture for today.